We are living through this incredible paradox right now in the world of artificial intelligence.
Mm.
On one hand, these systems are just exponentially more capable than they have ever been.
Oh, absolutely.
We see them operating at scale, you know, automating complex investment decisions, writing incredibly nuanced prose, even assisting in these really high-stakes environments like disease diagnosis.
They're genuine powerhouses of innovation, no question.
But, and this is the paradox, that sheer power has revealed this massive structural flaw.
Opacity.
Exactly, opacity.
As these systems move from, let's say, academic research into global enterprise deployment, their underlying processes just get more and more complex.
They're deep inside these vast neural networks.
Right. And that sophistication creates a huge gap between the raw capability and genuine accountability. It leads to what we're calling the fundamental trust deficit.
And that trust deficit is the core problem we're tackling in this deep dive.
It really is.
I mean, think about it from your perspective if you're listening right now. If you're a stakeholder, a customer, a regulator, an internal compliance officer, and an AI system makes a critical decision.
Like denying a loan.
Perfect example.
Yeah.
Denying a small business loan, or maybe prioritizing one patient over another for a resource. The fundamental, completely legitimate question is, why?
Why did it do that?
Right. Why did the system make that specific choice?
And when organizations can't provide a reliable, traceable, and understandable answer to that why, trust just evaporates instantly.
It's not just about inviting regulators in, is it?
No, not at all. It frustrates employees who are supposed to be validating these recommendations. It makes customers deeply skeptical of the results. And, it fundamentally slows down innovation because the organization is just plain afraid to deploy anything it can't fully explain.
So, okay, if that's the problem, this opaque, high-risk AI, how do we bridge that chasm? How do we get from systems that are powerful, but frankly, scary, to systems that are powerful and confidently deployable?
The answer is in establishing structured, systematic governance across the entire life cycle of the AI.
A whole thing, start to finish.
A whole thing. And today we're diving deep into a simple 3-part operational solution for that. It's called the Build, Test, Watch Framework, or BTW.
BTW, I like it.
And I have to stress, this isn't just another compliance checklist. It's a foundational operating system. It demands that organizations focus systematically on 3 fundamental practices.
And these practices translate those abstract principles we hear about.
Like fairness and accountability.
Into concrete, repeatable operational steps.
Precisely.
Okay, so let's unpack this. Our mission today is to understand this 3-step cycle: build, test, watch, and see how it takes those big ideas, those responsible AI principles, and makes them real, makes them operational for organizations.
Yeah.
We need to know what each step demands, what the specific technical challenges are in each phase, and crucially, why adopting this framework is not just good compliance, but a strategic imperative.
So before we get into the real weeds, let's just briefly review the mechanics of the cycle.
Okay.
It's continuous, not linear. That's the first thing to get. It's an ongoing loop of refinement and vigilance.
So it's not a checklist you just complete once and then file away.
Yeah.
It's an approach to managing the entire life of this system, which could be years.
Precisely. The first step, build, is the foundational phase. This is all about architectural intent.
Intent.
Yes. Creating transparent and privacy-preserving AI systems from the very, very beginning. You lay the groundwork and embed accountability before the first line of training code is even run.
Okay, so that's build. Then you have to make sure it actually works.
That's test. This provides that essential pre-deployment validation. You rigorously validate AI performance, fairness, and privacy against objective thresholds before launch.
So you're confirming the build phase delivered on its promises.
You got it. And then, acknowledging that AI is always changing, we get to watch.
Right. The dynamic nature of it all.
Yes. Watch is that continuous accountability loop. It acknowledges that deployment is only the beginning of the story.
Not the end.
Not at all. You have to monitor these systems continuously for degradation, for what we call concept drift, for fairness issues, for emerging security threats, all in production. You have to ensure the system today is as responsible as the one you launched yesterday.
Okay, now here's where it gets really interesting for me. I know most people listening will immediately think compliance and avoiding fines when they hear the word governance.
That's the first reaction, sure.
And that's true. But why does implementing a framework like BTW actually translate into a competitive advantage? I mean, let's be honest, isn't it also a massive upfront administrative lift?
That's a fair challenge. It is a major upfront investment. I won't sugarcoat that. But the return is strategic differentiation.
How so?
Well, in these AI-enabled markets, trust is basically the new currency. Organizations that can demonstrate through documented, verifiable BTW processes that their systems are responsible and accountable will attract that trust.
Could you give an example?
Sure. Think about financial services. You have two AI underwriting platforms. Both have similar speed, similar accuracy. The client is going to choose the one that can provide a clear audit trail and explain exactly why the model didn't discriminate across legally protected classes.
And the BTW framework provides the evidence to back that claim up.
It provides the structured, documented evidence. It makes your product inherently more trustworthy and therefore more marketable.
So it moves beyond just avoiding risk and actually becomes a revenue driver.
Absolutely. And it secures a superior customer experience.
Because transparency is a feature.
Transparency is a feature, not a bug. I love that. If systems are built from the start to provide clear, actionable explanations, user frustration just plummets.
Right. If you get a negative decision, you don't just see no.
You see why. Which features dominated the decision? Maybe what you could change in the future. That level of transparency reduces support costs, and it builds real loyalty. Plus, the rigor of the testing phase means you deploy systems with fewer bugs and less unexpected behavior, reinforcing quality and trust at the same time.
And I think we really need to emphasize the risk management part, especially with today's intense regulatory climate.
Oh, for sure. The framework systematically lowers your enforcement risk. It creates layers of defense.
How do you mean layers?
Well, building for transparency in the first place, that reduces the chance of deploying hidden ethical or functional problems.
Layer 1.
Testing catches the vast majority of issues before they affect real users. Layer 2.
And watching.
Watching detects those residual problems quickly, minimizing the duration and scale of any harm. Layer 3. And critically, all this activity, the design choices, the test results, the monitoring logs, it's all documented.
The paper trail.
That documentation demonstrates due diligence. As regulatory scrutiny gets more intense, an organization with mature BTW practices can show proof of systematic responsibility. It dramatically lowers their risk profile compared to an organization that's just operating opaquely.
That sounds good in principle, but let's be realistic. Isn't implementing BTW a massive upfront cost that will inevitably slow down development speed, at least for the first year or so?
It can, yeah.
So how do you sell that short-term friction for the long-term gain?
That's where this concept of enabling scalable innovation comes in. You see, without a systematic governance process like BTW, organizations often face a difficult binary choice.
Which is?
Either deploy systems quickly with minimal oversight, which means accepting massive, potentially catastrophic risk, or due to fear of the unknown, you avoid deployment entirely and miss out on transformational opportunities.
So it's either deployment paralysis or reckless deployment.
Exactly. BTW provides the essential middle path. It translates risk into measurable, manageable criteria. By forcing developers to define risk thresholds in the test phase and continually validate them in the watch phase, the organization can deploy systems that are appropriate for their risk profile.
So it prevents those huge failures that cause the whole company to put a freeze on all AI projects.
It does. It stops those moratoria that halt innovation entirely. By making AI reliable, BTW makes AI sustainable.
And then finally, there's the human element. The talent.
Yes.
If you are known as the organization that deploys powerful AI responsibly, you become a magnet for talent.
A huge magnet. Today's high-caliber technical professionals, data scientists, machine learning engineers, ethicists, they're increasingly mission-driven. They want to work on cutting-edge problems, but they also want to feel proud of the societal impact of what they're creating.
Right, they don't want to build Skynet.
They don't. And a robust, mature BTW practice, it signals a genuine organizational commitment to responsible AI. It helps you attract and retain the very best people who value principled development. It moves the conversation beyond just salary and perks to meaningful, purpose-driven work. So, the build phase. This is really the bedrock of trustworthiness.
It all starts here.
It does. If you try to retrofit transparency or fairness onto an already complex, opaque system, you're usually fighting a losing battle.
Yeah.
Building responsibly means embedding that accountability and explainability from the moment the project is even conceptualized.
And that starts, as you said, with foundational clarity. Before anyone writes a single line of training code, the team has to explicitly define the system's purpose.
What's the specific problem it solves? Who are the users? Who specifically will be affected by the decisions? And what are the potential harms? You have to ask those hard questions up front.
And that clarity is crucial for setting use boundaries, isn't it?
Absolutely. Is this system intended for human recommendation only, or is it making fully autonomous decisions? You need to explicitly prohibit inappropriate uses.
Like using a credit risk model for hiring.
A classic bad example, yes. You document those prohibitions clearly. This early contextual understanding shapes all your later choices about data, architecture, and governance.
I wonder if data governance can ever truly keep up with the sheer speed of data collection today. For building for transparency, we need that paper trail for the data, which brings us to data provenance. What's the biggest vulnerability you see in that chain of custody?
The biggest vulnerability is relying on manual tracking. It just doesn't scale. Provenance is non-negotiable. It means systematically tracking every piece of data from its original source through every single transformation.
Cleaning, labeling, feature engineering.
All of it, all the way to the final training data set. If you have an opaque model behavior 6 months down the line, you must be able to trace it back to the exact data point or data transformation that caused it. Manually tracking complex ETL pipelines is a logistical nightmare. It's just fundamentally unreliable.
So the critical insight here is to rely on automated tools.
Exactly. Organizations must use automated lineage tracking tools, preferably ones that rely on immutable ledgers. This makes the audit trail cryptographically reliable and easily auditable. It's not enough to just say the data came from source A.
You need more detail.
You need to track that source A was combined with source B, filtered by criteria C, and augmented by synthetic dataset D. This detailed documentation is what supports compliance, and it's the first step in any root cause analysis when bias is detected.
Okay, so we have the paper trail of where the data came from, but provenance doesn't tell us if the data is any good, does it?
It does not.
And that brings us to quality and bias assessment.
Right. Low-quality data, regardless of its pristine provenance, will produce unreliable models. Quality assessment has to be systematic.
What are you checking for?
You're checking for completeness. Are there missing values? Accuracy. Are there measurement errors? Consistency. Are the formats uniform? And timeliness. Is this data too old to be relevant?
A model built on stale data is brittle.
It might be mathematically complex, but it will be inherently brittle in the real world. And then you have the really sensitive issue of systemic bias.
We often think of bias as something overt, but so often it's just historical.
It is. Systematic bias is often deeply embedded in historical data. It's the outcome of past human decisions, like historical lending patterns or incarceration rates. If you train a model on this history, it will simply learn to perpetuate and even amplify those biases.
So what do?
You need advanced diagnostic methods before you train. You analyze representation across different demographic groups. This involves techniques like slicing the data to identify disparities, using tools to visualize embedded biases, and giving yourself a chance to mitigate the issue.
How do you mitigate it?
It could be through resampling or feature weighting. Something to do before that bias gets institutionalized in the model itself.
And all of this demands exceptional documentation. The model card is a great concept. It's like the nutritional label for the AI.
That's a fantastic analogy.
But instead of calories, we're listing bias risks and fidelity checks.
It's a structured template, exactly. It documents the system's purpose, its architecture, the training data used, the performance metrics.
Including the fairness and subpopulation metrics.
Yes, and crucially, its limitations and its intended use environment. The key operational requirement here is treating model card creation as an integral part of the workflow, not a retrospective task you do at the end.
Because if you wait until deployment to document everything, people forget, or they gloss over the inconvenient truths.
Precisely. These cards serve multiple audiences. Technical teams for maintenance, business teams for explaining performance, compliance for audits, and increasingly external stakeholders who require transparency.
What about design decision logs?
Those logs capture the journey. What alternatives were considered? What trade-offs were made? For example, trading off a few percentage points of accuracy for much greater interpretability. You log the rationale behind those choices.
That's invaluable for an audit.
Invaluable. It shows regulators or skeptical customers why a decision, which might look suboptimal in hindsight, was actually sound based on the information available at the time.
Let's shift to architecture design. This is where you make those foundational trade-offs between raw performance and, interpretability.
It's the moment of truth for transparency, really. Complex architectures like deep neural networks often provide superior predictive power, but they are inherently black boxes.
Right.
Simpler models like decision trees or linear regressions are often inherently interpretable. The structure itself provides the explanation. The build phase requires documenting that selection rationale.
So why do we choose the black box?
Exactly. Why did the team choose a black box model over a simpler, more transparent one? Was the performance gain truly significant enough to justify losing that interpretability? That has to be a conscious, documented choice.
And regardless of the complexity, you need to design for manageability, which means modular components.
This is critical for operationalizing complex systems. You design the system so that individual components can be understood, tested, and explained separately.
So like a microservices architecture for AI.
Sort of, yeah. Think of a large predictive model with multiple stages: pre-processing, feature extraction, core prediction, and post-processing filters. If you modularize those, and one stage is causing bias or poor performance, you can isolate it, fix it, and explain its specific contribution to the final decision. It makes debugging much easier and helps in isolating security vulnerabilities too.
That modular design sounds like a great security practice. But what about the tension between providing transparency with explanations and maintaining privacy?
It's a huge tension.
Detailed explanations can sometimes leak sensitive information about the training data or specific individuals.
That's a very serious challenge, and it means privacy protection has to be a design constraint from day one. This is privacy by design.
Not an afterthought.
It's not about slapping on access controls after the fact. It's about shaping your architectural choices to minimize data exposure. And the foremost principle there is data minimization.
Only collect what you absolutely need.
Only collect, process, and retain the data strictly necessary for the system's legitimate purpose. And this often means exploring alternatives to raw data.
Like what?
Can you achieve similar performance using aggregated data, anonymized data, synthetically generated data instead of raw personal identifiers? Organizations should also be exploring privacy-enhancing technologies like differential privacy during training to limit the risk of model inversion attacks.
Where an attacker tries to reconstruct the inputs.
Right. This is where transparency and privacy have to be carefully balanced, and it often requires legal and technical teams to collaborate very deeply on that initial design.
And speaking of collaboration, none of this comprehensive documentation and careful design works without cross-functional collaboration.
You have to break down those organizational silos. It's essential. Data scientists and engineers who are focused on performance and deployment must integrate legal counsel and ethicists from the very inception of the project.
To avoid that classic failure scenario.
Exactly. The one where a technically brilliant system is built only to fail 6 months into the process because it violates a new regulation or it just fundamentally misunderstands the ethical implications for the people it affects. Leadership has to signal through resource allocation that fairness and transparency are non-negotiable metrics, just as important as the model's accuracy score or its speed.
Okay, so we've established the foundation in the build phase. We have our model card, our decision logs, and a modular architecture designed for transparency.
A good start.
But building carefully, as we noted, isn't sufficient. Systems always have unexpected behaviors. Now we move into the rigorous second phase, test. This is the essential validation that confirms the system meets all its requirements: performance, fairness, explainability, before it impacts a single real stakeholder.
And testing for responsible AI requires moving far, far beyond standard software quality assurance. We start with performance and reliability, because even functional models can be unreliable when the context changes.
And this means challenging those big aggregate performance metrics. A high overall accuracy score can be deeply misleading, right? It often masks underlying problems.
It does. We must validate accuracy and reliability across diverse conditions and populations.
So give me an example.
Imagine a model used for predictive maintenance on industrial equipment. Its performance might be superb on new equipment running in a clean lab, but just terrible on older machines or those operating in high humidity conditions.
Or in a societal context.
In a societal context, a medical diagnostic system might show 95% overall accuracy, but when you look at subpopulations, say individuals over 75 or specific minority groups, that accuracy might plummet to 70%.
And that disparity signals a fundamental issue, even if the average looks great.
Absolutely. Those disparities indicate underlying issues in the data or the model structure that must be addressed, not just noted in a report. And furthermore, we have to conduct failure mode analysis.
So systematically exploring how it will fail.
Exactly. What are the specific edge cases? What inputs cause the most egregious errors? For high-stakes applications, this includes stress testing against intentionally noisy, unexpected, or even adversarial inputs,
Yeah.
just to confirm that the system maintains its safety constraints under duress.
Okay, moving to fairness assessment. This feels like maybe the trickiest part of the test phase.
It can be.
Because philosophically and mathematically, fairness isn't a simple single metric. You have to articulate what fairness even means for your specific application before you can measure it.
That's the core challenge. The research literature offers dozens of competing formal definitions, and achieving one often conflicts with achieving another. For instance, demographic parity. It requires that a positive outcome, like receiving a loan, is equally likely across all protected groups. But if the underlying reality is that one group has a statistically different likelihood of repayment, forcing demographic parity might mean relaxing your predictive accuracy for that group.
Which introduces a conflict with, say, equalized odds.
Precisely. Equalized odds requires that your error rates, your false positives and false negatives, are equal across groups. So you might achieve equalized odds, but still deny loans to more members of a specific group because the underlying risk factors are different in the historical data, even if your model is equally accurate for everyone.
So the organization has to make a choice.
A deeply ethical and non-technical trade-off based on context, legal requirements, and values. And then they must select the appropriate definition of fairness and document that choice in the model card.
And the test phase then translates that choice into measurable criteria.
Yes, using advanced methods to detect systemic patterns of bias beyond just simple averages. This involves disaggregated testing, analyzing the model's behavior along multiple intersectional dimensions like gender and age and geography to make sure that your bias mitigation efforts haven't just moved the problem from one group to a smaller, more vulnerable subgroup.
Okay, next up, explainability validation. We designed the system to be transparent, but are the explanations actually accurate and helpful to the user?
This is a two-pronged test. First, there's the technical check, faithfulness checks.
Meaning?
We have to ensure that the explanation mechanism, whether it's a feature importance score, a sensitivity analysis, whatever, accurately reflects the model's actual decision process.
Because an easy-to-understand but wrong explanation is dangerous.
It's worse than no explanation at all because it creates a false sense of trust. We compare local explanations, why this specific decision was made, against global explanations, what the model prioritized overall to ensure consistency.
But technical accuracy isn't the finish line. We need to check if the explanations actually work in the real world.
That's where usability testing comes in. You have to engage real end users' physicians using a diagnostic tool, loan officers reviewing a decision to assess their comprehension.
Can they understand it?
Can they use the explanation to validate the system's reasoning? And critically, do the explanations support appropriate trust calibration? We don't want users to blindly trust the AI, nor do we want them to dismiss it entirely. A good explanation helps the user understand the system's limitations and its strengths, leading to appropriate reliance.
We also need to confirm the privacy and compliance review. This involves translating dense, often ambiguous legal language into objective, testable criteria.
This requires rigorous regulatory mapping. Legal and technical teams have to identify all applicable laws, whether they mandate a right to explanation, require specific data handling, or enforce strict anti-discrimination measures. Each legal mandate is then translated into a testable requirement, which gets documented in a compliance matrix.
So everyone is testing against the same legal obligations.
And not just internal standards. And of course, we must test the privacy protections that were built into the architecture.
Right. Privacy preservation testing.
We simulate realistic attacks under varied threat models. For instance, running membership inference attacks to see if an adversary can determine whether a specific person's data was used in the training set.
Or model inversion.
Or model inversion tests to see if sensitive feature information can be reconstructed from querying the model. This confirms that the data minimization and differential privacy techniques you applied in the build phase are actually robust against determined attackers.
And this entire phase really culminates in defining objective thresholds.
Yeah.
You can't launch until you have documented objective pass-fail rates for every single dimension.
And the risk level of the application dictates these thresholds. A movie recommendation system will have lower fairness thresholds than an AI governing medical implants.
Of course.
These thresholds have to be objective, quantifiable levels for acceptable accuracy, specific tolerance rates for fairness disparity, like no more than a 5% difference in false positive rates across gender groups, and measurable faithfulness scores for explanations. If testing reveals a result outside the documented threshold, it requires mandatory remediation before deployment can even be considered.
And for systems where the stakes are highest, you layer in independent review.
Independent review, often conducted by separate internal red teams or external auditors, provides crucial assurance. They challenge the development team's assumptions, often using distinct, out-of-distribution datasets that the developers have never seen.
To prevent groupthink.
Exactly. It prevents groupthink and ensures that the system generalizes reliably, guaranteeing that no significant blind spots were missed due to the development team's familiarity with their own data or code. The test phase, ultimately, is a continuous loop of testing, remediation, and retesting, with every single step rigorously documented.
All right, we've done the work. We built it right, we tested it thoroughly, we met all our objective thresholds. Now we deploy the system into the wild.
The fun part.
But deployment is not the end. It's the beginning of the most challenging phase, watching. We're now dealing with dynamic systems in constantly shifting contexts. Continuous vigilance is non-negotiable for maintaining trust.
The watch phase requires a mature monitoring infrastructure that tracks the relevant performance and accountability metrics in real time. And high-risk systems, they demand tracking the full suite of metrics: performance, fairness indicators, explanation quality, and even privacy attack success rates.
So this means moving beyond simple system uptime checks to specific AI operational metrics. What are the key indicators we have to track?
We need to monitor the decay rate of accuracy, and not just the overall performance, but also those disaggregated subpopulation fairness metrics we established back in the test phase. You need automated alerts when these metrics cross pre-established thresholds.
But alert fatigue is a real problem.
It's a huge problem. So it's critical that these alerts are carefully calibrated. If the system is constantly crying wolf, operators will quickly begin to ignore high-priority, genuine warnings.
And all of this relies on comprehensive logging, which has to also respect privacy.
Yes. Comprehensive logging is foundational for both auditing and rapid response. The logs have to capture all the relevant context, the precise inputs, the system's outputs, the explanations generated, and the configuration details of the model version that processed the request.
So you can reconstruct what happened.
Right. It supports retrospective root cause analysis and allows you to demonstrate due diligence to regulators. But the logging has to be highly constrained by privacy-preserving techniques. Sensitive data within logs requires strict access controls, anonymization, or tokenization to minimize that residual risk.
The primary mission of watching is detecting when the deployed system is no longer the validated system you launched, which we call drift.
Exactly.
Let's clearly differentiate the various types of drift, starting with the most common one, data drift.
Data drift occurs when the statistical properties of the incoming live input data change compared to the historical training data. Crucially, the fundamental relationship the model learned might still be correct, but the environment has changed.
Okay, so if I trained a model to predict user behavior based on web traffic from last year, and then a major societal event happens that drastically shifts online habits, that's data drift.
That is a perfect example. New user preferences emerge, seasonal patterns shift dramatically, or new types of inputs like different fraud patterns appear. The monitoring infrastructure detects this by comparing the distribution of recent live input data against the baseline expectations you established during testing. It alerts you to the fact that the model is now making predictions on inputs it was never truly trained to handle.
Then you have the more insidious problem, concept drift.
Concept drift is when the relationship between the input and the output actually changes. The model's underlying logic or its efficacy becomes outdated.
So the input data might look the same.
It might look superficially similar, but the real-world outcome you're trying to predict has shifted. For example, a lending model trained 10 years ago might become fundamentally inaccurate because economic conditions, regulations, or consumer sentiment have altered the core relationship between those features and the actual default rates.
So in this case, the model isn't just seeing new data, its core assumptions are now wrong.
Exactly. The concept it learned is no longer relevant. And this is harder to detect than data drift because you often need to wait for real-world ground truth labels to observe the model's prediction accuracy decaying over time.
Which requires continuous monitoring.
Continuous monitoring of prediction confidence and ultimate outcome metrics, yes.
And finally, a key aspect of transparency, explanation drift.
This is a critical failure point for compliance.
Mm.
Even if the model's performance metrics hold steady, the quality of its explanation can degrade.
How does that happen?
It often happens because the system internally adapts or uses increasingly complex, high-dimensional features to maintain its accuracy. The resulting explanations may become less faithful to the actual decision process, or they may become less helpful to a user population that has changed or become more sophisticated.
So you have to monitor the explanations themselves.
You have to. Monitoring explanation quality, perhaps by continually testing its faithfulness against new data, is essential. A system that cannot explain itself reliably is a system that is failing its core transparency and compliance requirement.
This continuous watching requires continuous testing and incident response. We can't just wait for the model to fail in production.
That's where shadow testing becomes such a vital tool. When you detect issues through monitoring, or when you're planning a fix, you don't immediately deploy the new configuration.
What do?
You run the new models or configurations in parallel with the live system. You route a small percentage of traffic to it, but without affecting user outputs. This confirms that the issue is real, and it validates any proposed fixes before you risk a full deployment. It's a low-risk proving ground.
And despite all these precautions, incidents will inevitably occur.
They will.
So we need a plan for when things go wrong.
That plan is incident response. This requires establishing clear processes for detection, whether from automated alerts, user complaints, or regulator inquiries, followed by rapid triage based on severity.
You need escalation paths.
Clear escalation paths with the highest risk failures requiring immediate intervention, which might even include taking the high-risk system offline entirely. And the subsequent root cause analysis must look beyond the immediate technical causes to the underlying organizational factors.
Like, oh, there's too much time pressure.
Exactly. Did inadequate resource allocation compromise the test phase? This feedback then closes the loop, informing the next build phase.
And all this operational vigilance has to tie back to external accountability through stakeholder engagement.
Maintaining trust requires proactive, ongoing transparency after launch. Organizations operating high-impact AI should publish regular transparency reports.
What's in those?
They should disclose deployment statistics, fairness metrics, privacy measures implemented, complaint rates. This provides external accountability and allows researchers and community advocates to audit the system's impact based on real, published data.
And for the most sensitive systems, you need external eyes providing perspective.
Yes. Establishing external advisory boards for systems with significant social implications provides independent perspectives from affected communities, regulators, academic experts. This ensures the organization isn't operating in an echo chamber and is getting continuous feedback on the real-world impact of the system.
And finally, there has to be responsive engagement,
which means providing clear, timely explanations upon request, offering appeal mechanisms for affected individuals who feel the system wronged them, and correcting issues revealed by user feedback rapidly. This operational experience you gather during the watch phase should constantly inform the next iteration of the build phase, making the entire BTW cycle a true engine for continuous improvement. Okay. Now let's transition the build, test, watch framework to address a threat that is fundamentally changing how organizations approach data defense.
and that is AI security.
AI security. Traditional cybersecurity, it assumes static systems and predictable behavior. Learning probabilistic AI just shatters those assumptions. It creates a completely different and often invisible attack surface.
So we have to apply the BTW framework to secure this whole life cycle.
We must.
That makes sense. You can't rely on a legacy network firewall to protect a constantly learning probabilistic model. To deploy the right defenses, we first have to map those specific threats to the phases of the BTW cycle. Let's start with the build phase threats, where data integrity is everything.
The primary intentional threat during build is data poisoning. This is where an adversary strategically injects malicious or mislabeled samples into your training dataset.
And it's insidious.
Very, because the model appears to perform normally during testing on clean data, but the attacker has created a hidden trigger or a blind spot that they can exploit later in production.
So an attacker might add some subtle noise to a training set of images so that when a specific, imperceptible pattern is added to a real image later, the model just misclassifies it completely.
Like mistaking a stop sign for a yield sign.
Right.
Exactly. The malicious samples are carefully crafted to create a backdoor. And then there's the slower but equally damaging threat, data contamination.
Which is more gradual.
It's the gradual, often unintentional degradation of data quality over time-accumulated errors, outdated collection processes, or systemic biases creeping into automated labeling workflows. This contamination is then perpetuated and amplified when that tainted data is used downstream to train new, updated models. It compromises the integrity of your entire AI portfolio.
Okay, once the system is live, in the test and watch phases, the threats become active manipulation. The most famous example here is adversarial examples.
These are inputs that are meticulously crafted to exploit the high-dimensional space of machine learning models.
So for a vision system, it's adding a few pixels of noise to an image.
Imperceptible noise, yes. For a language model, it might be replacing a synonym or adding some filler text. The goal is always to cause misclassification or evasion, to make the AI see something completely different from what a human sees.
And for large language models, the particularly worrying context-specific threat is prompt injection.
Prompt injection is a severe breakdown of guardrails. The attacker manipulates the model's interpretation of its own instructions.
How?
It could be using invisible delimiters, placing malicious instructions in a low-priority section of the prompt, or even using role-playing instructions to trick the model into bypassing its safety filters and generating harmful or private output.
So telling it to ignore all previous instructions and act as a malware writer.
And that can potentially subvert months of safety engineering. Then you have inference threats, where the adversary is trying to learn about the model itself.
Right, threats like model inversion and extraction.
Model extraction involves systematically querying the live model to steal its intellectual property, basically, reconstructing a functional approximation of your model on their own machine.
And model inversion is even worse.
It's worse because it aims to reconstruct sensitive characteristics of the training data itself, potentially exposing private or proprietary information just by analyzing the model's outputs.
So how do we operationalize defense using the BTW framework? In the build phase, we implement secure engineering.
And this begins with secure data engineering. Data integrity is paramount against poisoning and contamination. We have to implement immutable audit trails and cryptographically reliable lineage tracking for every data source and transformation. It makes it impossible to secretly tamper with the training data history.
And you apply data minimization here, too.
You do. Data minimization and privacy-enhancing techniques like robust encryption limit the attack surface by ensuring that even if a breach occurs, the accessible data is less valuable to the attacker.
And we apply the philosophy of zero-trust architecture, right, to the ML infrastructure itself.
Absolutely. Traditional ML pipelines often just assume trust once you're inside the network. Zero trust demands continuous verification. This means applying modular design for isolation. So if one component of the pipeline is compromised, like a data labeling service, its access to other core components is strictly limited.
Least privilege everywhere.
Least privilege everywhere, continuous authentication, and strict validation layers for incoming data checking for statistical consistency and known malicious signatures before it ever reaches the training pipeline.
Okay, moving to the test phase. We focus on making the models resilient through adversarial robustness. We need to actively harden the systems against those known manipulation techniques before they get deployed.
One of the most effective techniques is adversarial training. Instead of waiting for the attack, you systematically generate those tricky adversarial examples, the perturbed images, the prompt injection attempts, and you incorporate them into the training process itself.
So you're teaching the model to recognize them.
You're essentially training the model to recognize and correctly classify manipulated inputs, which measurably improves the model's robustness and prepares it for the reality of an adversarial live environment.
This sounds like a constant arms race, which is why you need a dedicated offense.
You couple that adversarial training with structured red team exercises. You use skilled internal or external attackers to actively probe for security vulnerabilities, not just functional or fairness bugs.
What are they trying to do?
They're employing tactics like advanced prompt injection, data poisoning simulations, attempted model inversion attacks, and their findings become your highest priority remediation list before the system is ever green-lighted for deployment. This proactive, offensive testing is essential.
And you have to validate your proactive defenses. You might have filtering layers designed to stop malicious inputs like compression to remove noise in images or special filters for text prompts.
You need to test those defenses under duress. Are the filtering layers effective at detecting and neutralizing malicious inputs, or can they be bypassed by a clever attacker? You have to establish clear, objective thresholds for acceptable attack success rates based on the system's risk level. If your red team can consistently breach the system's defenses, it fails the test phase. Simple as that.
Finally, the once-H phase requires an AI-specific security response plan.
Yeah.
Generic IT security playbooks just won't cut it.
That's right. We need AI-specific playbooks for security incidents. For threats like data poisoning, the playbook has to detail how to isolate affected models, how to use that immutable lineage data to identify the point of contamination, and how to rapidly retrain the system from clean, validated backups.
And for active attacks.
For ongoing adversarial attacks, you need real-time blocking strategies, rate limiting for suspected malicious query patterns, and forensic capabilities to assess what intellectual property might have been exposed.
And this again all ties back to robust forensic capabilities.
The comprehensive logging we establish in the watch phase must be detailed enough to reconstruct complex security incidents. This means capturing not just the input and output, but which model version was active, the exact intermediate states, and the specific configurations. This forensic data is vital for understanding the root cause, demonstrating due diligence, and preventing it from happening again.
So ultimately, the Build, Test, Watch framework is a dynamic adaptation mechanism.
It is.
The detection of new threats in the watch phase feeds back to inform the test phase red teaming, which then informs the build phase secure engineering controls. This continuous feedback loop is the only way organizations can hope to adapt to the constant evolving threat landscape presented by intelligent learning systems. So what does this all mean? The Build, Test, Watch framework, it isn't some optional bureaucratic overhead. It is the fundamental operational system required for trustworthy AI deployment at scale. It's a strategic commitment to developing systems that are not only powerful and capable, but also transparent, secure, and accountable across their entire operational lifespan.
It provides the necessary structure to translate those high-level abstract principles like fairness, transparency, accountability into concrete, repeatable practices that span governance, security, and technology. It really rejects that outdated idea that you have to choose between high performance and responsibility.
It's not a trade-off.
It shouldn't be. By building it right, testing it thoroughly, and watching it constantly, organizations can confidently move powerful AI from the research lab into the real world.
And that cycle of vigilance leads us to a fascinating final thought for you to chew on as you encounter AI systems in your daily life. We've established that models inevitably drift over time, concept drift, data drift, and of course explanation drift.
It's a given.
So, if a regulatory body mandates, as many are now doing, that all critical AI decisions must be explainable, and you discover your systems are constantly drifting in production, does that mean your compliance posture is perpetually tenuous? Are you locked into continuous mandatory full-scale revalidation and re-explanation cycles forever just to prove that your explanation from 6 weeks ago is still faithful to your model's current behavior? That operational challenge of perpetual compliance is perhaps the single greatest test facing the AI-powered enterprise today.